Hello, my name's Michael Kinsey, and in this talk I'm going to give an overview of some methods for determining the number of repeat simulations for evacuation and pedestrian modelling. In the talk, I'm going to talk a little bit about what are random values and how are they generated. I'm also going to talk about why we use random values within evacuation pedestrian models and where they're typically found within the modelling environment. And then going to dive straight into giving an overview of the key methods for determining the number of repeat runs. I'm also going to talk a little bit about potential methods for reducing the number of repeat runs as well. So what is a random value and how are they generated? Well, essentially a random value is a sequence of numbers that contain no recognizable patterns or regularities that cannot easily be reasonably predicted better than by chance. And the way you can assess whether a sequence of numbers is random is through a series of statistical methods to assess how random the number sequence is. Now, anything that's developed by a computer is technically not guaranteed to be random, and the methods of assessment are generally based around recording how frequent patterns of numbers occur in distributions. So computer programs have pseudo-random number generators or libraries which are typically passed a seed value, and then this is used to produce or calculate a random number, commonly between 0 and 1. Now, Mass Motion uses the Boost Random Library, and this is either by using the MT19937 generator, or where performance is more critical, it will use the RAND48 generator. And typically the random seeds within Mass Motion can be specified by a user or a previous simulation run if required. By comparison, other evacuation or pedestrian models may use the system clock to define the random seed for a given simulation. So why do we use random values in evacuation or pedestrian modelling? Well, there are three main reasons we use them. The first is there's actually just natural variability in human behaviour. To give an example, if we were to evacuate a building and we record the results, if we were to reproduce exactly the same evacuation with the same people in the same initial locations, we'd actually expect to find slightly different results. And this is because people may make slightly different decisions, and these small differences can have a ripple effect on the overall results. The other two reasons that we use random values is one is because we have a lack of understanding regarding the initial conditions prior to the time a simulation starts. We don't actually know, if I have to do an evacuation model for a building, I don't actually know for a real evacuation how many people are actually going to be in the building. I don't know how many people perhaps they're going to be. I don't know initially exactly where they're going to be located. I don't know all people's past experiences prior to an actual evacuation. So there's a lack of understanding regarding the initial conditions. Now, in addition, there is a lack of understanding generally about how people behave, and it's very hard to answer the question about certainly things to do with decision making. How do people make certain decisions? Because often people make decisions that they're unaware of. So these are the three main reasons why we use random values. Now, for each of these aspects, random values are utilized in various forms to influence various parts of a simulation. So, for example, in terms of defining the initial conditions, so perhaps where people are, their walker speeds, things like that, typically distributions are defined. And quite often these distributions may be found in standard guidance documents telling you should be using these distributions to represent people in an office, for example. Also, researchers often conduct research trials, experimental trials, or analysis of how people behave, and they typically produce their results as distributions. And basically, whenever time that a distribution is used, quite often the way you sample that distribution, or you assign an agent a speed or something from a distribution, is that you randomly sample it. You say, I've got a 50% chance of using perhaps a 50% bin within a probability distribution. So they're randomly sampled. Now, because they're randomly sampled, it introduces variation in the simulation results. So the reason we need to run or repeat run a number of scenarios in evacuation pedestrian models is to represent the full range of key behaviours possible which are influenced by random sampling that have a significant impact upon, one, the modelling results, and two, the wider project decision-making process that inform the design. Now, it's important that you consider both of these in the decision about how many repeat runs you need to do, because quite often people only look at number one here. They'll only say, oh, look at it, how much of an impact it has on the results. But actually, certain types of behaviour, even if they have a big impact on the results, may actually have very little impact upon what decision you're going to make based on the overall analysis. So it's important to think about different levels of consequence within the process. So in terms of when random values are actually used, I've listed some here. These are common places where you might find random values or random sampling used in evacuation and pedestrian models. So the first one is the initial starting location. So typically agents may be randomly located within a building or on a floor plate. You might guide this in some respects, so you might have a certain number of people on each floor. Route assignment, you may say that 30% of people use route A, 30% use route B, 30% use route C, and 10% use route D. So you may actually manually guide people to do things. Now typically that might be using random assignment, because when you say 30%, actually it only means you've got a 30% chance of it happening. It doesn't guarantee that that number will occur. That number of agents will be assigned to use a given route. Sort of on a related note to that, you can supply weights to route selection algorithms to say how important different aspects of a route selection of the route selection algorithm is. And mass motion uses weights associated with route selection. So this might be another place where we might find random sampling, where there's a distribution associated with weights and they randomly sample from that distribution. We may assign agents tasks. Again, you randomly assign a proportion of agents will use a given perform a given task. Walker speed is very common, so you have a distribution of walker speeds and it randomly samples from there. Awareness of modeling elements, the proportion, the likelihood of someone being aware of, say, signs or a given exit. Assignment of task completion times, so pre-evacuation time is a very common one for evacuation modeling. Again, normally it's defined as a distribution, and then that's randomly sampled. And then resolution of conflicts space. So if two agents are vying for the same space, the system, because we don't have a great understanding about how people resolve conflicts when they're going for the same space, the system might just roll a dice and say, right, whoever's got the highest number will take the space. In terms of methods for determining the number of repeat runs, I've listed 5 here. The first is brute force, second is fixed number, then dynamic assessment of variance in output variables, and then qualitative visual assessment. In addition, you can adopt a hybrid of these, a combination of one of these. In addition, I've listed some methods to reduce or potentially remove the number of repeat runs. Now, with evacuation pedestrian modelling, quite often simulation run times aren't a huge impact, certainly in the work I do anyway. So this is perhaps of less interest, but it's something which is good to be aware of. For each method, I've listed a description, a criteria of when perhaps it may be used, and also the benefits and limitations. So I'm going to first start by talking about methods to determine the number of repeat runs. So the first one I'm going to talk about is a brute force method, and essentially this works by you keep running repeat simulations of a given scenario until all distributions with every permutation have been suitably sampled for all of the underlying distributions and wherever you're using random sampling. Now, when might we use this? Well, you may use this when time or computer resources are not overly constrained. You may also use it if the model has built-in automated functionality to test previous samples, because it becomes very labor intensive if you want to go and test whether all your permutations have been tested by a person. It's almost not even possible. Typically, this may be an option if you have a numerical simulation, for example, or some kind of classic Monte Carlo simulation where running the sample, running a scenario multiple times won't take very long. In terms of the benefits and limitations, it's great because it will ensure all potential behaviors are sampled, if indeed they actually get sampled. One problem is that you could be running repeat runs, and it could never converge. It can never sample certain places just because of the way the random sampling is working. And it's reasonably simple to program this method. Now, there are quite a reasonable list of negative aspects associated with this method, and indeed most of the methods I'm going to be talking about actually have a longer list of cons compared to pros. So the first negative aspect of this method is it can potentially take a large amount of time to complete. It may never also fully sample all distributions. It will likely create a large number of files to analyze, which can create a bit of a pain, or maybe it'll take a bit longer to actually get the results out that you need from the overall simulations. It's not a very scalable solution as well, as you increase the number of simulations. So the number of repeat simulations will exponentially grow with random sample usage. Also, if you add in more distributions, it will again make the whole problem a lot bigger. It's also expected to create a high degree of redundancy when the necessary repeat runs, because you'll be trying to sample all of your values in a distribution, but actually maybe they have very little impact upon the overall results. The next method is the fixed number method, and this is basically where you decide how many repeat simulation runs you're going to run before you've even run any simulations. Now, you might use this where a code document requires you to do this. So IMO 1238, the International Maritime Organization codes for evacuation model validation verification, specifies you should run 50 simulations. You may also run this when it's expected the random sampling has a little impact. So I might run this if I might fix a small number of runs just to demonstrate that it has very little impact. The random sampling has very little impact upon our model results. You may also run this when the fixed number is expected to capture all types of behavior. You think it's reasonably big to capture most types of behavior also. In terms of the benefits and limitations of this method, it's simple to understand, it's simple to codify and program in models. The downside with this method is it's uncertain if appropriate number has been completed to represent all behaviors. It also does not consider simulation results. There's no two-way coupling here between the simulation and the number of runs. And it can take a long time with big models, and could potentially cause unnecessary runs. The next method is a dynamic assessment of variance in an output variable or series. This method effectively keeps running repeat runs of a simulation, and then it assesses the variance in an output variable or series from the simulation and then compares it to a summarized value. And then it says if this value, if the proportional difference or some kind of difference, if a given difference between those two values is found, then it will run another run, and then it constantly updates, and then eventually it'll say, oh, there's a given boundary condition which it doesn't pass, so we'll say we're not getting any more variance by adding on more repeat runs, so that's we don't need to run any more. So we may use a single variable to assess, so for example the total evacuation time of an evacuation simulation, and I might just look at how much the variance has changed by adding in another repeat run results. Conversely, I may look at a series of numbers, so for example the evacuation curve you can see in the graph here, and I might compare the actual shape of the graphs, and that's what these equations here do in that you can see here on the top of the top right hand slide. A good paper for looking at comparisons of different series to determining the number of repeat runs is by Enrico Ronchi and a few other people when they were working at NIST. The reference is here. In terms of when I might use this method, we may use this when a more detailed consideration of repeat run variance is required. There may be a code document which requires you to do this method. I'm not aware of any which do actually ask at the moment, but I may expect this to happen perhaps in the next few years or so. It's also, you might use it when there's expected or is uncertain if random sampling will have a substantial impact upon the rate of a given variable. You may, if you think there's going to be a very big difference in the evacuation rate, this is a good way to compare them. In terms of the benefits and limitations, this can result in a lower number of repeat runs compared to fixed method, because there's a feedback process whereby you're looking at the simulation results and you're comparing it to your past simulation results. So it gives some consideration to the results. This said, it only considers a single point or series of the results. So it only considers a symptom of the random variables, random sampling that you're utilising, and it's uncertain if all key behaviours is represented. It also requires you to determine a threshold of acceptance to be defined, which can be a bit arbitrary. So you have to define, what is the proportional variance which I'm prepared to accept. The final way for assessing or determining the number of repeat runs is just to use a qualitative visual assessment, and this effectively works by you keep running repeat runs and then you visually look at them. You compare where agents are in the simulation at given times in order to determine whether they look very different, and if you think they look approximately the same, then you document that process. So when might we use this? Well, you might use this where agent movement can be easily compared between runs. You may use it when you've got small or simple simulations with expected small number of runs. You may have an evacuation or pedestrian model which allows viewing of repeat run simulations in one view. So mass motion allows you to overlay repeat simulations and where agents are in one view. So this is a great way to see if things look very different. It also may be used in a combination of another method. So quite often we would run a number of simulations and we may adopt a fixed number, but then we'd also do qualitative visual analysis or assessment to just check whether the results do actually look very different. In terms of the benefits and limitations, this can be reliable to identify the impact of random sampling on agent locations, and it gives some consideration to simulation results. This said, it is hard to consistently apply between different users and scenarios. So if I had two people doing exactly the same job, they may rank the difference between different simulations slightly differently. So attaining consistency with this method is quite difficult. It also relies on users understanding evacuation dynamics and where random sampling is being used. If you don't understand how the numbers are being generated, then it's very hard for you to accurately interpret how the results may be affected. It's also hard to keep track of large numbers of agents, so this method is perhaps particularly challenging to apply where you've got larger numbers of agents, possibly doing complex tasks as well. Now I'm going to briefly talk about methods to potentially reduce the number of repeat runs for evacuation pedestrian modelling. The first one is I've termed conservative value assignment. It's nothing to do with David Cameron, the ex-British Prime Minister, but what it is focused on is about specifying specific random variables as static conservative values to represent the worst case scenarios. So this is particularly a method that could be employed within evacuation models, and it works on the premise that if you're assigning everyone, instead of using a random distribution of something, you assign everyone the worst value from that distribution, and then if the results still work in the underlying decision-making process, and it doesn't inform your decision anymore, or it doesn't get any worse, or if it still passes your acceptance criteria and with the worst case values assigned, then you actually say, well, I don't need to run any more repeat simulations because I know it works for the worst case. Now such assignment will, in terms of when we use this, you have to decide whether the results are still going to be plausible but still represent conservative behavior, and this requires a certain degree of user expertise, because if you assign everyone a very slow, for example, assign everyone a very slow walker speed, is it actually still going to produce realistic results? Now, in certain situations, especially in evacuation modelling, we already use conservative values to factor in or manage uncertainty. So that being just apply. If you're employing it already, then maybe it's of no impact. Also, you have to understand that if you are changing values, you have to be sure that it's going to have a negative impact upon the results. In terms of the benefits and limitations, well, the benefit is obviously it can reduce the variation in repeat runs, so thereby reducing the number of required runs. In terms of the negative aspects, it can result in unrealistic or potentially overly conservative behaviour. It's only really appropriate to apply to single or small number of variables, because the minute you start applying it to multiple sets of variables, it can just become very hard to keep track of where everything is. And again, it goes back to perhaps it's going to produce unrealistic behaviour. It obviously requires a user expertise and understanding the full impact upon the simulation results of conservative assignment, and it can result in over-redundancy in the design process. The final method for potentially reducing the number of repeat runs is to use something called guided sampling or Latin hypercube sampling. And this is a process whereby you instead of randomly sampling from a distribution, you actually guide the sampling of the distribution such that it ensures that the entire distribution is fully represented by considering previously sampled values. So if I have say a probability distribution, I may discretize the distribution up into different bins, and I know how many people I would expect in each bin, and then I would make sure that number is found in each bin, so I fully sample that distribution. Now, in terms of when we can use this, so I can guarantee that my distribution is going to be represented for the first scenario, first simulation run. Now, I'd use this when, first of all, we need to be aware of the number of samples we're going to take before we sample the distribution. Now, with some some distributions, it's fairly simple to know that. For example, walker speeds. I know how many people I've got in my simulation before the simulation starts, so I know how many walker speeds I'm going to assign. Often we could potentially apply this when the number of distributions and the population are small, and it's easy for a user to manually perform this task in assigning agents these speeds. In terms of the benefits, this can reduce variation in repeat simulations, so reduce the number of repeat runs. The downsides of this method are, due to multiple distributions commonly being used, it can still result in a large number of runs of all permutations required, so we can still end up with having to run quite a large number of runs. Also, the order in which you assign people within the distribution will impact the results. So if I've got a walker speed distribution, and I've also got the location, if I assign agents a slow walker speed but a location close to an exit, they will exit very quickly. But if I assign people a slow walker speed and they're far away, then they will take a long time. So the order in which I assign agents relative to the other random distribution that I'm sampling can impact the results. It can generally only really be used where we've got a distribution of data that we need to sample from, though in theory we can apply some kind of spatial Latin hypercube sampling also. In terms of what we may expect in the future in terms of determining the number of repeat runs, this is all based on my own sort of thoughts. I probably expect to see more inclusion within codes regarding guidance of evacuation and pedestrian modelling, to be more specific about what they want us as modelers to do. At the moment, there's very few codes which actually have this information in. I may expect better methods for comparing different repeat runs to come about. So one method that you might potentially look at is comparing actual agent locations, X, Y, Z coordinates, between different repeat runs. This can actually quantify the actual differences between spatial locations of agents between repeat runs. And again, you set your thresholds, and if it doesn't vary by a given amount after you keep doing repeat runs, then you can stop running. And also we may expect a more hybrid solution, so whereby we use multiple ways to assess variance within repeat runs. So in summary, statistical distributions with random sampling are used to represent aspects of initial conditions or decision making in evacuation and pedestrian simulations. Random values introduce variance in repeat runs of a simulation, so multiple runs are commonly required. A number of methods exist to determine the number of repeat runs, and some are stated in some standards, but it's by no means widespread. There are also some methods to exist to reduce the number of repeat runs, although generally, in my personal experience, these generally aren't that too much of use, because it doesn't take very long to run lots of different repeat runs, certainly not for medium-sized models anyway. I would generally recommend that you always produce results of multiple repeat runs, even if this has a little impact, in order to demonstrate the range of variability or impact is low. I've done reviews of other projects before where people have only ran one simulation and said, oh, I didn't notice any results, so I didn't run anymore. But if this was going to, for rigor, we should be running at least a small number to demonstrate that it's of low impact, rather than just saying we thought it was. That's the talk. Thank you very much.